Partial fraction decomposition can be very complicated. So what I'm going to do today is walk you through a couple different examples and give you some rules to follow so that you can get through these problems okay. The first thing we want to do is write a partial fraction decomposition for this expression on the left. So that is the given. And what we want to do is we want to write it in terms of this expression on the right, but we need to find what A and B are so that that works. So in example 1, they have given us the setup. Normally, we would just have the left-hand side as the problem. They got the right-hand side by factoring the denominator. When we factor the denominator on the left, we get x minus 3 times x plus 2. So those are the two factors that are going to be in the denominator. So those are going to be each denominator for the two fractions on the right side. Now I want one to be x minus 3 and one to be x plus 2. I don't know what goes on top of those fractions, so I call one A and I call one B. What I am trying to do in a partial fraction decomposition is I am trying to take this rational function on the left and break it into a sum of rational expressions on the right. So I found the denominators on the right. I do not know the numerators. To find them, I am going to solve this equation for A and B, and the algebra is going to get pretty complicated. Step 1, go ahead and multiply the entire equation by the common denominator. The common denominator is x minus 3 times x plus 2. So on the left side, the whole x minus 3x plus 2 cancels out with the denominator, and all I am left with there is x plus 7. So the left side of my equation says x plus 7, and that's it. On the right side, when I multiply this entire denominator to the right side of the equation, I'm going to go to this one first. For the first fraction, the x minus 3's will cancel, but I will still have an x plus 2. So I have the A from the top, and this x plus 2 gets distributed to it. Let's do this again for the second fraction. Now what I'm going to do is I am going to multiply this entire denominator to the last fraction. When I multiply it to the last fraction, the x plus 2's cancel. I still have this x minus 3, and I still have what's on top, a b. So I have a b times an x minus 3. What I have done is I have created an equation to help me solve for A and B. The problem is I have 3 variables in one equation, which can be difficult to solve. So here's what we're going to do. We're going to distribute on the right-hand side and call it AX plus 2A and BX minus 3B. And then we are going to group like terms. And here's what I mean by this. On the left side, I have one x. On the right side, I have an ax and a bx. So that one x is generated from the ax and the bx because those are the like terms from that side. Those are the x terms on the right side. So I'm going to write a little mini equation over here that says whatever a and b are, the ax and the bx I know will total up to a 1x. You can divide both sides by an x and really get a little equation that says whatever A and B are, they need to equal 1. Whatever A and B are, they have to equal 1 so that the AX and the BX add up to a 1x. If A is 5 and B is negative 4, I will get a 1x. I am going to do the similar thing with the constant. So now I'm going to take the constant 7 and I'm going to say, where does that come from? Well, that comes from this positive 2A and this negative 3b. So 7 comes from a 2a and a minus 3b. What I have done here is I have created a system of equations. Go ahead and solve that system. Give me the answer for both a and b. The answer you should have gotten, you can use substitution would be fine. A equals 1 minus b, and then sub it into the other equation for the a value there, or you could use elimination and line them up. I don't care. But the answers you should get are A is 2 and B is negative 1. Now remember, the problem did not say find A and B. The problem said write the partial fraction decomposition. So my solution at the end here is that this fraction on the left can be broken up into A, which is 2 over x minus 3, plus B, which is negative 1 over x plus 2. And this is a partial fraction decomposition. Now, this gets difficult because of all of the different ways of setting up in that very first step that we didn't have to do. The setup was given to us here, but that part can be really tricky. So here's some rules. If you have a linear factor in the denominator, so x minus 3 was a linear factor and x plus 2 is a linear factor because there was no exponent on those x's. If you have a linear factor in the denominator, then above it, you will always put a constant. So that's what we did in example 1. Above x minus 3, we put an A. Above x plus 2, we put a B. So anytime it's linear on the bottom, you put a constant above. If it's a quadratic on the bottom, so if you have an x squared in the denominator, then you would give it a linear numerator. So you would do a whole ax plus b or a whole cx plus d or whatever. If you have a repeated factor, so if I had x minus 3 twice, x minus 3 squared, I would call that, then what I have to do is I have to give that multiple fractions, and the power of the denominator increases with each fraction. Let's see if we can look at examples of all the different setups. First thing I want you to do on example 2 is factor that denominator completely. Now that you've factored the denominator completely, you should have an x, and then the x squared plus 2x plus 1 factored as x plus 1 squared. I have two different types of factors here based on my rules. I have an x, which we'll consider to be a linear factor. So that one will go with an a on top. And then I also have an x plus 1 squared. So the x plus 1 is also a linear factor, but the squared makes it a repeated factor. So we're going to write this x plus 1 squared. We're going to write it twice. And the power is going to increase. So the first time it's to the power of 1, and the second time it's to the power of 2. That's how a repeated factor works. Now, these are all considered linear factors, x plus 1, and x plus 1 repeated. So I just put a letter above, an A or a B or a C. Now, the rest of my process is the same as we did in example 1. You are going to start by multiplying this entire equation by the common denominator, which is what you got when you factored in the very first step. Whenever you multiply this, you multiply it to every single fraction it gets distributed in. It needs to always cancel the entire denominator on the left. So the whole denominator on the left is gone, and the left side just says 5x squared, 20x, and 6. The right side, though, it will not eliminate everything. You'll have some more stuff there. So let's see what happens. The a over x, the x's cancel, and you have a x plus 1 squared. So we have an a x plus 1 squared. The second fraction with the b, we're going to cancel 1x plus 1 with 1x plus 1. So we have a b, an x, and an x plus 1. So we have b times x plus 1. I am just clearing fractions here. For the last one, the whole x plus 1 squared cancels, and you have just the c and just the x all together. Now this one looks harder. I think it's actually going to be easier than example 1. Let's see what happens. Leave the left side. On the right side, go ahead and distribute and simplify. You are going to first FOIL this, and then distribute the a in, distribute the b in, combine like terms. Go ahead and do that now. Hopefully what you got was ax squared, 2ax, a, bx squared, bx, and cx. Now, let's go ahead and match our corresponding terms. I have a 5x squared on the left. I have an ax squared on the right and a bx squared on the right. So a and b have to total that coefficient, which is 5. I am just looking at the coefficients of the corresponding terms. A and b have to be 5. Let's go ahead and look at all my x terms. I have a 20x in the middle, and I have a 2ax and a bx and a cx. So I have a 2a and a b and a c. That's going to add up to the coefficient, which is 20. But check this out. My constant 6 is a, because on the right side, a is the only constant. Well, if a is 6, then I can plug that in here, and I find very quickly that b is -1. If b is -1, then I plug that in here. Go ahead and do that and tell me what c is. Beautiful job. C is 9. Okay, great. We got A, B, and C. That's not our answer. Our answer is the partial fraction decomposition. We have 6 over x. We have -1 over x plus 1. And we have 9 over x plus 1 squared. That is your solution to this partial fraction decomposition problem. Want to try another one? Let's move on. On the back side, again, they did the setup for us. When you factor out this denominator all the way, you get x and x squared plus 4. The x is linear, so that's going to get an a over x. It just gets an a on top, fine, no problem. The x squared plus 4, you cannot factor anymore. That's what we're referring to when we say a quadratic factor, which was the second one of the rules in the box. That's a quadratic factor, x squared plus 4. So on the top of that, we give a linear factor, bx plus c. We proceed in the same way. So we're going to multiply this entire equation by x times x squared plus 4. The left side, we are going to cancel the entire denominator, and we get 3x squared, and we have a 4x, and we have a 4. The right side, we're going to first cancel those x's. So we have an a times x squared plus 4. For the second fraction, we are going to cancel the quadratic, the x squared plus 4. So we have a bx plus c. Don't forget those parentheses around that factor, and that will get distributed by the x, which was left that didn't get canceled. Go ahead and distribute to get ax squared, 4a, bx squared, and cx. What do you know right away off the top of your head? You are right. C has to be 4 because that's my only x term on both sides. So I can identify immediately C is 4. Similarly, A has to be 1 because 4a is the only constant. It has to equal 4. So a has to be 1. You can also tell me that ax squared and bx squared give you the 3x squared. So a and b equal 3. So plug in that a as 1. You'll find then that b is equal to 2. And make sure that you give me the answer to this problem, which is the broken up fractions, aka the partial fraction decomposition. So our answer is actually 1 over x plus 2x plus 4 all over x squared plus 4. So I am just undoing that fraction addition there. One more problem today. This is part B. I would like you to try the setup. Pause me, write the setup on your paper, and then continue this video. What we have here is we have a quadratic factor, x squared plus 2, that can't be factored anymore, and it is being squared. So we are calling this a repeated quadratic factor. If it's repeated, remember, then we include it that many times. So we have x squared plus 2, and we have it again. But the power increases. So the first time it's a power of 1, and the second time it's a power of 2. Since those are both considered quadratic, the top of those need to be linear. So an ax plus b, and we'll give the other one a cx plus d. See if you can solve this entire thing out, multiply through by the denominator, go through and solve, see if you can get your final answer and type that in for me.